Hello, this is my 6th video where I do real analysis proofs. It's the 4th video in which I am focused on what I'm calling fundamental inequalities. In this video, I'm going to suppose that I've got two positive real numbers, c and d, and a natural number, n, also called a positive integer, 1, 2, 3, 4, 5, 6, etc. I want to prove an if and only if statement, which means I need to prove two things. I need to prove that if c to the n is less than d to the n, it will follow that c is less than d, and vice versa. If c is less than d, then c to the n is less than d to the n. Among the various ways this could be done, including some ways using calculus facts, which I'm not going to want to use here at the beginning of a real analysis class. I'm going to assume I don't know anything about derivatives. We will first verify this factorization that you see here. And I'm going to do it in a special way. I'm going to use the formula for a finite geometric series. I have an ulterior motive here. I want you to know the formula for a finite geometric series before proving the fact above. Then we will use this factorization, to prove that fact above. In fact, very quickly, once I have this factorization, you might briefly think about how that would be done very quickly. This factorization, by the way, should look somewhat familiar. In the case where n is 2, it's the formula for the difference of two squares. In the case where n is 3, it's the formula for the difference of two cubes. So there is also a formula then evidently for the difference of 2 fourth powers, 2 fifth powers, 2 sixth powers, etc. Second note is that the result of this problem implies that at least over the interval of all positive real numbers, the open interval from 0 to infinity, also thought of as the set of all x, real numbers x that are positive, this function x to the n, which is a power function with positive integer exponent, and its inverse, the nth root of x, are strictly increasing functions over that set, and they are inverses over that set. All right, so I think I'll go ahead and state the formula for a finite geometric series as part of the proof. I'm going to assume it's true. Of course, the formula for a finite geometric series itself would need to be proved, which I will not do here. You could use induction to do that. By the way, coming back to this equation, certainly you could try to verify it by multiplying this out to see that you get this after a bunch of cancellation, though to do so would require steps where you need to use the distributive property and commutative property. It's kind of tedious. You might try to prove it with induction. You might try to prove it with long division, although that's not really so much of a proof as a technique to discover it in the first place. But I'm going to assume that we know the formula for a finite geometric series. And if you don't, this is a good review, or it's good to learn it for the first, right away for the first time. Recall the formula for a finite geometric series. Geometric series are very special kinds of sums that have a lot of important applications in the real world, in science, in finance. In fact, I make a lot of videos about actuarial math, in particular financial math. Right now, in fact, that you might want to look up if you're interested in being an actuary. Recall the formula for a finite geometric series that a plus a times r, these are real numbers here, although this formula actually works for complex numbers as well, plus a times r squared plus a times r cubed, etc. I'm going to denote the last term by a times r to the n minus 1. Note that a is the first term. That's what it's called, in fact. R is the value that you need to multiply each term by to get the next term. It's called the common ratio, because if you take any term and divide by the preceding term, except for the first term, you get r. That's why it's called the common ratio. Also note that this has n terms in it. This will equal the first term, a, times, in parentheses, 1 minus this common ratio to the power equal to the number of terms here. I decided to put an n minus 1 as the highest power of r so that I have n terms. So this is a power of n. If I had made my last term a times r to the n, then this would be an n plus 1 here, because I would have n plus 1 terms. And this is all divided by 1 minus r, and I hope it's clear to you that this is true. Well, you would hope this is true as long as r is not 1. Okay, and if r is 1, then there's a different formula. You don't want to divide by 0 here. How am I going to use this? I'm going to focus on this part of the formula here and recognize that that is actually a finite geometric series. If I let A equal the first term of that sum, which is d to the n minus 1 power, and then let R equal what would be the common ratio. What do I need to multiply each term by to get the next term? Well, certainly you need to multiply by a C. Think about it, you also need to multiply by 1 over d. I am assuming C and D are positive real numbers here, so I'm not dividing by 0 if I do that. Let R equal C over D. D is not 0. I also don't want R to equal 1. In the proof, C will be less than D, so R will not equal 1. Though this equation here for this factorization is true when C equals D anyway, because then both sides are 0. By the formula above, once I've made those definitions, I can say that d to the n minus 1 plus d to the n minus 2 times c plus d to the n minus 3 times c squared, etc., plus d squared c to the n minus 3 plus d c to the n minus 2 plus c to the n minus 1 is equal to, use this formula with a equal to d to the n minus 1, r equal to c over d, to get this. Now I am still using facts about algebra. In your head, imagine now, well, use the distributive property, first of all, on top, to get d to the n minus 1 times 1, which is d to the n minus 1, minus d to the n minus 1 times c over d to the n. We are, still using properties of algebra here, and I'm not going to bother saying I'm using properties of algebra here. That's pretty obvious. I know I talked about using that to actually do this expansion. But I did want to show you the formula for a finite geometric series because that's useful in a lot of things in real analysis. So we get this after using the distributive property on top, and you can say distributive property if you want. And then, using the fact that I can multiply the top and the bottom by d, really multiplying the whole fraction by 1, I'm multiplying by d over d, this simplifies to d to the n minus c to the n over d minus c, right? Because you get cancellation. D times d to the n minus 1 is d to the n. D times this, the d's cancel, giving you c to the n. D times 1 is d. D times this, the d's cancel to give you c. This is equivalent after multiplication of both sides by d minus c, and I am assuming d is not equal to c here. To the factorization, d to the n minus c to the n equals d minus c times, I won't bother writing all this again. I've got it up here if you want to see it. Okay? At least when d is not equal to c, but again, when d equals c, this factorization is trivial. Both sides are 0. That's worth mentioning if you were actually doing an official proof. I can make some comments here. When d equals c, the equality that I'm writing right here, equality is trivial. Now this equality, you can't do this equality when d equals c, but this equality is true trivially when d equals c. Though in the final proof of the statement we're after, I'm assuming d is not equal to c. So now we're ready to do the proof of the actual thing we're after. I could do this part of the proof in terms of double implications, if and only ifs essentially, but I will write it two ways. If d to the n is less than, do it the other way around. If c to the n is less than d to the n, then d to the n minus c to the n is positive. Save some writing here. You should mention that this part, this thing right here, is positive because I'm assuming C and D are both positive. C and D are both positive real numbers. So this expression that I just circled, which is also going to be down here, is always positive. So again, I'm not really writing this proof in the most ideal way for sake of time. That's always positive, so that if d to the n minus c to the n is also positive, that implies that d minus c itself must be positive. So the equation above, maybe you want to give this equation a number or something, equation 1 above, implies d minus c is positive, so c is less than d. On the other hand, if c is less than d, this logic completely reverses itself. Then d minus c is positive, so the equation above, if you've got this always being positive, no matter what c and d are, as long as they're positive real numbers, and if you're assuming this is positive, the product of two positive real numbers is also positive. This implies d to the n minus c to the n is positive, so c to the n is less than d to the n. And basically we are done there. Okay, so I could have written this a little more cleanly. You probably should if you had a problem like this on a homework problem. But this, to avoid using calculus, this probably is the best approach. And again, I'm assuming I know this formula. You might consider trying to prove this formula for a finite geometric series using induction. We have done proofs involving induction. I'm assuming that's true. I use it here, and that gets me to this factorization, which is the most useful thing to use without calculus to prove the thing that we are after. Again, that does also imply that both of these functions are strictly increasing over the interval from 0 to infinity, and you might want to think about why that is the case.